Alright, thanks for watching, and today I will present you another really cool proof for which you only need calculus. Namely, I will show you that the number or the letter E is irrational. And the cool thing is, if you look back, or if you're too young, you look forward to all the calculus courses you've taken, in fact, so far you've never used the fact that E is irrational. Which means that we're allowed to use all the calculus facts that we know about E. In particular, we're allowed to use the Taylor series expansion, or they call it Maclaurin series expansion, of E to the x. So maybe just a preliminary step. One thing you should know is that E to the x can be expanded as the sum from 0 to infinity of x to the n over n factorial. And this expansion, it's valid for every x, and therefore we can just plug in x equals to 1. So E, which is e to the 1, would be the sum from n from 0 to infinity of 1 to the n over n factorial, which is just the sum from n from 0 to infinity of 1 over n factorial. And in other words, it's a cool identity. If you take the reciprocals of all the factorials and you sum them up, you in fact get E. And I'm claiming so that this expansion gives you an irrational number. So 0 from infinity of 1 over n factorial, and claim this is irrational. Alright, now let's get started with the proof. So step 1. In fact, before showing that it's irrational, let us show that in fact E is not even an integer. Which is, again, it's surprising because so far E could be an integer. We've never not shown that. So claim E is not an integer. And in fact, this is not too bad to show because look, why? Well, again, don't laugh at me, but 2, that is 1 plus 1. Okay? But 1, if you want, is 1 over 0 factorial plus 1 over 1 factorial. And this is strictly less than 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus blah blah blah. But this is precisely E. Okay. So E is strictly bigger than 2. And let me also show you that E is strictly less than 3. So, no. But for this, we just need the following fact. So note, if you compare n factorial and 2 to the n, well, at like n equals to 1, this is bigger than that. But eventually, n factorial becomes much bigger than 2 to the n. So in particular, if n is greater than or equal to 4, then n factorial is greater than 2 to the n. If n is greater than or equal to 4. And the reason is, what is 2 to the n? It's 2 times 2 times 2 times 2 times 2 n times. But n factorial, it's okay, 1 times 2 times 3 times 4 times 5 times 6. So at every step you're multiplying by a bigger number than 2. So if n is large enough, this should be eventually much bigger than that. You can also prove it by induction, but that's a completely different topic. Okay, so what is E? Then E is, again, 1 plus 1 over 1 factorial, plus 1 over 2 factorial, plus 1 over 3 factorial, plus 1 over 4 factorial, plus, just for fun, it's 1 over 5 factorial, etc., etc. But the point is, from what I said here, n factorial is eventually bigger than 2 to the n, which means that 1 over n factorial, it's smaller than 1 over 2 to the n. Okay? And therefore, from this part on, we can have a comparison. So this is strictly less than, if you want, 1, I guess 1 plus 1 plus 1/2 plus 1/6. So this is a boring part, but the interesting part comes here. So 1 over 2 to the 4th plus 1 over 2 to the 5th plus 1 over 2 to the 6th, etc., etc. So the interesting thing here, we actually get the tail of a geometric series. So if you want to factor out 2 to the 4th, so this thing, by the way, it's 8/3, I believe. And then plus 1 over 2 to the 4th times 1 plus 1/2 plus 1/4 plus blah, blah, blah. But again, by a geometric series, this sum equals to 2. So we have 8/3 plus 1 over 2 to the 4th times 2. So 2 over 2 to the 4th. And that becomes 8/3 plus 1 over 8, if you want. And the thing is, 1 over 8, that's less than 1/3. So the point is, this eventually becomes, less than 3. So, not I love you, it's less than 3, even though I do love you. Thank you. Okay, so, after that, okay, what have we actually shown? We've shown that, on the one hand, e is greater than 2, again, because it's some positive terms. But we've also shown here that e is less than 3. So e is strictly between 2 and 3, so it cannot be an integer. Unless you could come up with a cool integer between 2 and 3, at least on Earth, this is not true. Okay, and in fact, we will need this fact for a proof. So now let's actually now show that e is irrational. So step 2. What would it mean to be rational? It would mean that e is a fraction of two things. So suppose e equals to a over b, where a and b are integers. And moreover, we've just shown that e is positive, so we can assume a and b are positive. And of course, b is not equal to 0. But also, think about this. If b equals to 1, then e would be equal to a, which is an integer, but then e would be an integer. But we've just shown that e is not an integer. So we can also assume that b is not equal to 1. And this will be useful very soon. Okay, so great. So e is a fraction of two integers, positive, and then the denominator is neither 0 and 1. And just recall from what I said, 5 minutes ago, we actually have that e is equal to a series. So recall, e equals to sum from 0 to infinity of 1 over n factorial. And in particular, because this is a series, we can truncate it and consider the partial sums. And in fact, those partial sums, they become the key to answering our problem. So, in fact, here's the cool thing. Given this b that we had before, consider the partial sum up to b. And we'll see what we have here. So, let x be the following. So, you truncate the series up to b, 1 over n factorial, where again b is as in e equals to a over b. So that b here. And moreover, let's consider not this partial sum, but if you want the remainder of the two. Namely, the actual series minus the partial sum. So, e minus that, which again becomes, if you want the error term, when you approximate e with this partial sum. And finally, let's just scale it a little bit for it to be useful. Let's multiply this by b factorial. Okay. So again, let's consider x to be that big number, and we wanna study this. In fact, this x, as I said, it becomes the key to solving our problem. So first of all, let's show that this weird number is an integer. So claim 1, x is an integer. And why is that? Well, remember that e is just a over b. So x becomes, if you like, b factorial times, again, e is a over b, so times a over b minus the sum from 0 to b of b factorial over n factorial. Oh, I skipped a step. 1 over n factorial. So remember that was our definition of x. And then let's just expand this out. So that's b factorial times a over b minus sum from n from 0 to b of now b factorial over n factorial. Okay, so there are two things to analyze. First of all, what is b factorial over b? Right, that's b times b minus 1, b minus 2, blah, 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 times 1 divided by b. This cancels out, and you're left with the product from b minus 1 up to 1. But that's just another name for b minus 1 factorial. So that becomes b minus 1 factorial times a. And notice, this is precisely an integer. And then now here is a cooler thing. Notice, we're summing from 0 to b, so n is in particular less than or equal to b. And here comes again the cool thing. If you have a bigger factorial over a smaller factorial, it actually becomes an integer. Let me just try to convince you with an example. Okay. Let's say, let's kind of calculate 5 factorial over 3 factorial. Well, what's this really equal to is 5 times 4, again, times 3 times 2 times 1, over 3 times 2 times 1, and that's equal to 20, which is an integer. So, the point is, we have this minus, again, this summing thing, but this is an integer. This becomes an integer. So, in fact, we have an integer minus an integer, which becomes an integer. So, what is an integer? X is an integer. Okay. So that was our first claim. And now we want to prove our second claim that will help us conclude that there's a contradiction. Second claim. In fact, x, which is an integer, is between 0 and 1. Okay? And notice, again, just as before, there ain't no integer between 0 and 1. So if we prove this claim, we have a contradiction. Okay? Contradiction with what? Contradiction with the fact that E is rational. So once we've shown this, this would imply that E is irrational. and then it would be done, and we can go home happy. But let's first show this. So I guess step 3. So we will show this in 2 parts. We'll first show that x is positive, and then x is less than 1. So let's first show the easy part. So x positive, for this you just remember the definition of x. X is b factorial times the sum, if you want, times e minus the sum from n equals to 0 to b of 1 over n factorial. But again, what is e? E is just the sum from 0 to infinity of 1 over n factorial minus the sum from n equals to 0 to b of 1 over n factorial. But look, here you're summing from 0 to infinity, and here you're summing from 0 to b. So what we end up with is precisely the tail of the series. So that becomes b factorial times sum from n, from the next term, b plus 1, to infinity of 1 over n factorial. And notice, because we're summing positive numbers, in the end, we get a positive number. So that's good. X is positive. And now, let's show that x is strictly less than 1. And interestingly, we only need this formula here. All right, now let's show x is less than 1. X is love, x is life. So show x is less than 1. And as I said, we will use the same formula. So remember that x is b factorial times the tail here, sum from b plus 1 up to infinity of 1 over n factorial. Put the b inside. So sum n equals to b plus 1 to infinity of b factorial over n factorial. Okay, and now we want to estimate this. We want to show somehow, that this tail here is strictly less than 1. And for this, we need an estimate, which is the one thing in math, the first time you learn it, you're like, this is weird and useless. But the more you use them, the more addicted you get to them. So notice, so if n is greater or equal to b plus 1, then let's look at b factorial over n factorial. Well, that really is b factorial times, maybe let's do it from the other side. You're going from n up to b. So if you want b plus 2, b plus 1, times b minus 1, times b minus 2, etc., etc. But that's just b factorial. So, in other words, you can write n factorial as the product starting from b factorial, and you just add as many products until you get n. And the nice thing is, this you can cancel out. And again, we've used the fact that n is strictly bigger than b. And so what you're left with is really, b plus 1, b plus 2, up to n. And the question, how many terms are there? N minus b plus 1 plus 1, and that's equal to n minus b. Okay, so the point is, there are n minus b terms. So in particular, notice this is strictly bigger than that, this is strictly bigger than that, and then n is at least greater or equal to that. So, really, because each term is strictly bigger than b plus 1, you actually get a less than thing. So 1 over b plus 1, b plus 1, up to b plus 1. And again, how many times did we do this? N minus b times. So in the end, you have strictly less than 1 over this first term raised to the power of n minus b. b plus 1 raised to the power of n minus b. And I guess I should put a less than or equal sign here, because it could be that n equals to b plus 1. Yeah. Okay? So the point is, all those terms, you can estimate it with this term here. And let's see how we can conclude from that. All right, here comes the grand finale. So what do you have? X is the sum from n from b plus 1 to infinity of b factorial over n factorial. Okay, and now we want to use that estimate. So in fact, this is less than or equal to the sum from n equals to b plus 1 to infinity of 1 over b plus 1 to the n minus b. However, one little remark, the only case where we get equality is in the particular case where n equals to b plus 1. So, in fact, in all the other cases we get a strict inequality. So in the end, we do have a strict inequality, and that's super important. So otherwise, proof might not work. Okay, and now let's see what that equals to. Well, if you let n equals to b plus 1, that becomes 1. So you're left with 1 over b plus 1. And then let's continue. 1 over b plus 1 squared plus 1 over b plus 1 cubed plus blah, blah, blah. And you may actually recognize that as a geometric series because b is just a constant. So 1 over b plus 1 becomes our ratio here. So if you want, you can write this as 1 over b plus 1, 1 plus 1 over b plus 1 plus 1 over b plus 1 squared plus blah, blah, blah. And that becomes 1 over b plus 1 times 1 over 1 minus 1 over b plus 1. And if you want, just multiply out the denominator. So this becomes 1 over b plus 1 minus 1. So that's 1 over b. And you may ask, hey, remember at the beginning I told you that b is not 0 and not 1? Where in the world did we need that? Precisely here. Because 1 over b, since b is not 0 or 1, this actually becomes strictly less than 1. And so in the end, what have we shown? We have shown that x equals to something less than something, blah, 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 and less than 1. I guess we didn't even need that because we had the other less than sign. But still, it's pretty cool. So, in fact, we have x is strictly less than 1. And therefore, because we have, again, x is strictly between 0 and 1, and x is an integer, in the end, we do have a contradiction. It's a very juicy contradiction, but on the other hand, what we've shown is that, in fact, the e is irrational. So that's pretty cool. And again, it's a neat proof because really all it uses is calculus. And then, it's cool. All right, so if you like that, and if you want to see more fun math, please make sure to subscribe to my channel. Thank you very much.